We are testing our understanding of momentum transfer, right? So, one, what is the mathematical expression of an incompressible fluid? Incompressible means that even if you try to apply a force on it, it doesn't change the density, right? So, writing that mathematically, we say d of the density of the fluid with respect to time is equal to 0, right? If there's 0, it means that it's the same as writing p, right? Same as writing density is constant. Right? That's what it means. Density doesn't change. When you compress it, it remains the same, right? So same as writing density is constant. All right, the next question. This one says what the following represent, right? So this here, see a minute. Okay. The first one, this one here means velocity in the x direction, direction that changes in x and y direction. Right, so that's what that one means. We're going to the next one. This b here. What this is Reynolds number. Reynolds number. That's for this. And the same for this. It's the same thing by different representation. This also is Reynolds number. So if you see any of them anywhere, represents Reynolds number. Right? And what of this? Is dynamic viscosity. Dynamic viscosity. And this is kinematic. Viscosity. Right. Viscosity. All right. And then this just by the way, but then know that these two here can be used to express this Reynolds number. There's a way. So Reynolds number can be expressed in terms of this or in terms of this. So let's take note of that. So you can check that out just for understanding. Okay. Here's another question. What is the mathematical expression for a steady state condition? All right. So what do we say a steady state condition is? I guess by now you've said it off head, right? But representation when we're writing the math is write steady state, right? So you write the quantity, the conserved quantity, and then this, and then we have this is equal to 0. This is what we call steady state, right? Another way of saying this this accumulation, right? So the conserved quantity, this alpha in brown here, doesn't change as the function of time. It's constant. That's always a steady state, right? And then the uniform state condition is where, depending on the coordinate system, you could have it this way. So you could have this. So let's say if we are talking about it depends. So if, let's say we are talking about it in a rectangular coordinate system. Rectangular system. Let's just say, okay, that will be this, right? The quantity changing. So let's make it this way. Because here we are taking on different things, it will be partial, right? Partial derivative. Rectangular coordinate system, one of the sides will be x, right? And then we have the conserved quantity changing post rectangular coordinate system y, and then we have the conserved quantity changing to z, all this equal to 0, right? What this means is that the conserved quantity alpha, right, if we say it's in a uniform state, that will mean that it doesn't change with respect to any of the sides of the coordinate system, right? So if it happens that we are dealing with a spherical coordinate, let's say cylindrical coordinate system, right, that will be r, right, and we'll have here z, right, and we'll have here theta, right? If you are talking about spherical coordinate system, and then we are saying that the system is in a uniform state, then we will have r here, and we'll have theta here, and we have, and it is an angle, we have another angle here, right? Yeah, that's if we are in the, sorry, should have changed this, right? So this one will be for spherical, and if it happens that we have a cylindrical coordinate system, it's cylindrical, then we have here to be r, we have here z, and we have here to be what? An angle, let's say theta, right? So yeah, okay, in the question. So the inventory rate equation, right, it's basically describing what's in the system, what's happening within the system, right? So we see that the rate, okay, it can be any which way, but just remember which is what, right? So we have the rate of generation, rate of generation of alpha, which is the quantity, right? Let's try this one. It can be every which way, but I just understand what's happening, right? And then writing the actual signs, whether positive or negative. So rate of generation, right, is a plus, and we have a rate of input. Let's rearrange it somehow. So we have a rate of input of the conserved quantity alpha, right? And then we have minus, right? We have a minus, that's a rate of output of what? The conserved quantity, and all this equals the rate of accumulation. Accumulation. And we've seen that the rate of accumulation is what of the quantity. Let's write it here. Conserved quantity A. The rate of accumulation is what at times we write as and so that's what we at times write as the partial derivative T of the conserved quantity, right? So this is another way of writing the rate of accumulation. So whenever you see this, that's the accumulation term. All right. Okay, so now we are defining the steady state and the uniform state in words, right? So we say this it's basically describing a system. So let's do it step by step. So let's say a system, okay, or a quantity. Let's say a conserved quantity. So a conserved, you can skip the conserved. Just put the quantity is said. So it's in steady state when it does not change with time at a particular point in space, right? So another way of saying this is that when you just hear steady, just know that we're talking about time, right? So just say a quantity is said to be in steady state if it does not change as a function of time at a particular point in space. So it's basically about time and space. So if it doesn't change with one, it changes with the other, right? So if it doesn't change with one, we see at a particular it's either we see at a particular time and it changes with the other at a particular point in space and change with the other. So this we are talking about steady state. We say a quantity is said to be in steady state when it does not change with time or is not a function of time. That's what it means at a particular point in space, right? But when we say that when we're talking about uniform, right? Uniform state, that means that, let's just write this short. It's a way of saying that at a particular point in time, right? At a particular point in time, uniform. When a conserved quantity is in uniform state, it means that at a particular point in time, it is not a function of space, or doesn't change with location, right? So that's what that particular one means. It does not change with location, right? And there's a way to actually illustrate this. So let's see if we can illustrate this. So what it means is that so now we put them side by side and talk about them. Right? So let's see. So on the left we have steady state, and on the right we have infinity. So let's say we have a system, right? Let's see, rectangular coordinate system, right? That will be center of the solve, right? So there's a rectangular coordinate system. So let's see. So here could be x, here could be y, and then here could be z. What this means is a steady state, right? Meaning that it doesn't change with time. So if I pick a particular position, right, within the system, right, let's say about here, right, and let's say 1 second. 1 second passes, I check. 2 seconds pass, I check. 3 seconds, 4 seconds. After almost any time, when I check the amount of the conserved quantity at that point, it does not change. At that point, it does not change, right? So that's what we see, that the conserved quantity is in what, or the system is in what, steady state, right? But then when we are talking about the uniform state, so let's see. Then again, let's use the rectangular coordinate system, right? So something like this. Okay. Oh. And again, the same coordinate system. So we have x here, y, and we have a z. Right. Coordinate system is very important because, like, if you miss that, it could mean like you are describing something else, right? So z. What the uniform state is saying is that uniform, right? Mean that's not a function of space at a particular point in time. So let's say it's not a function of space. So let's see two spaces, right? So let's say there's a 1 point here, there's another point here, right? If a particular coordinate system, so if I check, let's say 2 minutes, I check at 4 minutes, check again at 6 minutes, right? The quantities, right? Those quantities, the conserved quantities at these points are not changing, right? Though they are different positions in space, they are not changing, right? They are the same at this point, right? At this point, after I check it at 2 minutes, 4 minutes, 6 minutes, the quantities at this point, and even if I pick any point, the quantities there, let's see, here's A, here's B, here's C, here's D, and then here's E. At any point, the quantities at this point are equal, they are the same. So that's what we see, a uniform state, right? So that's what we're talking about here, right? So now let's go to this one. What does it mean when NRE is equal to is greater, sorry, less than 2,100? Right? So basically, what to be able to understand, you must know what this represents. As we've seen, this NRE here is the same as RE, which is Reynolds number. So if we have an NRE or RE, which is a Reynolds number, to be less than 2,100, then we are saying that we have a laminar flow. Laminar flow here. So that's what that means. That's what that means. So if it happens that we have an, let's say, N RE, which is same as RE we've seen, to be greater than 2100, then if it is this way, then we see that we're having a turbulent flow. Yeah, so that's what it means. Okay, now, so what are the flow regimes within a fluid, right? What are the flow regimes? So basically, the flow regime is that we have a boundary layer, and then we'll have the bulk fluid, or boundary layer, yeah, bulk fluid or bulk regime, as we see. What this means is that, let's say we have a conduit, right? So we are just looking at the inside. So let's say this is a cylindrical system, right? So if for that, the coordinate system for this particular one will be something of this sort. Right? Have this, and then we have this, right? Because we're talking about rectangular coordinate system. Here will be Z, right? And then here will be R, because rectangular coordinate system. So if you have a fluid flowing here, so let's use something else. Okay, so we have a fluid flowing here through this side, through this fluid. The boundary layer is the part where what's the name, the fluid is closest to the layers of the wall or the conduit that is flowing through. So within that region, you see the fluid is actually very close to the walls of the pipe, right? So it kind of like assumes the, what do you call it, the condition or the speed of the walls of the pipe. So because the walls of the pipe are stationary, or the walls of the conduit are stationary, the water will just closest to it within this thickness, right? Which we call the boundary thickness, boundary layer thickness. Most of the times you see a representation as this. Yeah, this is the boundary layer thickness. Within that regime, that's what we call the boundary layer thickness. But anywhere outside that, so this is for an internal flow, right? Because the fluid is flowing through, it's flowing internally through the conduit, right? Or what we are talking about, the fluid is flowing internal through it. So this is internal flow, right? So here to have a boundary layer here, but within this side is what we'll have for this particular condition. So we'll have a bulk fluid, right? So bulk regime, and then we have the boundary layer, right? Yeah. Okay. So now let's say that describe what is happening at the filling point, right? So here is the same thing. We're having a fluid flowing through a conduit. So the conduit could be about let's see here. So conduit could be here, right? This is the conduit. So yeah, let's use something else. Okay. The conduit will be this container here. So this is the inside. So this is basically internal flow, as we can see. So or it can be anything else. This could be a pillar of a bridge, and then the what do you call it? The fluid is flowing around it, right? So let's see. Okay. And then we've seen what the streamlines are already. So we are trying to describe what's happening at these points, right? So as the fluid flows, you see the direction that's coming from. Let's see. It flows here. Let's minimize this. Now we've seen the coordinate system already, so we can take this out. The coordinate system is very important. Very, very important. So there's one streamline of it. So what happens at this point here? So whenever a streamline, this is describing the flow of the fluid, it gets to this point here, it is stagnating. So by that we mean that it kind of like stops, right? Something like that for a while or so, right? Stagnate. Okay. So at point A, we have stagnation, right? What's happening at B, or the what do you call it, AB, right? So AB is seeing what's happening at this side. What do you think is happening? So you see that when it gets to this point, the streamline kind of like experiences an interference, so it kind of like bends, right? So when it bends here, so you see, let's use an example. So from here to here, there's the brown here, the brown line is the conduit, right? The wall of the conduit. So from here to here, it's a cross-sectional area. So that we are using a conduit, for instance. So what happens within any of this region, right? Between A and B, so look at it very well. You see that the cross-sectional area of where the fluid is flowing is small. And if you've seen this equation before, what we have, let's see. Oh, okay, let's write it here. What we have here, A. Let's bring it down. We have Q, A. That's not working. But okay. Well, we have Q and then A, and then we have another Q. We have another A. Here, yes, 1, 1, yes, 2, 2. Right. So the same fluid, the same volume of fluid or amount of fluid with this particular side here, right? Meaning it has a bigger area, right? So it will flow a little bit slow, right? But when it gets here and the area is small, it gets some kind of constriction, right? So the fluid accelerates at that side. So that's what it means. It's basically because of the area, the cross-sectional area at that point, right? So let's say here we have the fluid acceleration, right? Right? And now see what do you think is happening. B is at the point where you see the fluid. You see we still have the streamlines here, the streamlines. Okay, still have the streamlines here. So C is just about the point where the fluid or the fluid like or streamline separate from this obstacle here, right? So what that means is that if the fluid is flowing very fast, what did we see? We said something about boundary layer. So the boundary layer is where the fluid is, the area where the fluid is just attached, just close to the obstacle. It's having a contact with it, right? So because if the fluid is very fast, right, you see that the boundary layer will separate from the what do you call it, the obstacle, right after point C. So C, what happens at C is that the fluid, let's use the boundary layer. Okay, the boundary layer is basically the fluid. So the boundary layer separates, right? If the fluid, or to be more, let's use the right term. So let's see if fluid velocity is very high, right? Very high. So that's what's happening at that side. So for this, then we have this, and then we have this. Okay, and what's happening at BD? Then again, you can use the area again. So comparing it to this and comparing it to this, you see that here's the part where the area continues to decrease, decreasing cross-sectional area, right? So let's see. So here's more length, shorter length, more area, smaller, decrease, so accelerating. But when it comes here, the area that's from B to D, you have the cross-sectional area increasing, right? So if it's increasing, then it will be decelerating. With this side, right? Why? Because the area cross-sectional area is what? Increasing, right? So what happens here is that fluid decelerates. Yeah, so that's what's happening there. All right. Okay, so here we're saying that we are using the fact that the resultant force at a point within a fluid. So here basically is about fluid, right? So that's why we see hydrostatics, right? Hydrostatics. At a point S0, with the help of the figure below, derive the hydrostatic equation, right? So that's what I'm going to do. This is there. All right. Okay, so let's see. Because we are using this, we have to establish what a coordinate system, right? So for this case, what we are going to do is we establish our coordinate system, right? It could be nice already there, so this is already y, right? So but let's see, because we are using a rectangular coordinate system, for no tricky reasons, let's just see z here, right? So this will mean that we have dz. Let's use a different color. Laminar here, and we'll talk about what we are seeing here. Everything. So the main thing is that we have the coordinate system, right? And then if it's this way, and then we have x here. If it's rectangular, we have y here. That's why we have a y here. So now let's go on and talk about it. So the thing says is that we are using the fact that the resultant force at any point is 0, right? So let's see. Okay, so that will mean that we are considering just this particular volume of fluid. This is the whole bulk fluid, right? The whole bulk fluid, the whole bulk of the fluid. This all this, right? But then we are assuming that it's static, right? It's not shaking or anything, and it's not affected by any external force, right? So let's see. So within this fluid, we are considering a small portion, which is this kind of like a door here. But then we zoom in and we get a volume of fluid, right? That's what we are seeing, some sort of a box here. Right? So let's see. Okay. So that's what we are doing. We are choosing a conversion that up means positive, and then down is negative, right? So, and then we're talking about forces, right? So that will mean that, but then let's talk about the forces that are involved here. We know that when an object is totally or partially immersed in a fluid, it experiences what abstract. Right? So this term here is abstract, right? And then this one here is what we call body force, which is basically the weight of this small portion within the fluid that we are talking about, right? So that's abstract. Okay. And then this one here is basically surface forces. Right? So this P here is basically the forces that are acting on this as a result of the forces that are acting on the surface here. This dP here is as a result of the forces that are acting here, but that ends up in the moving this fluid, this force here in this down direction. So basically, you're talking about up and down. Now let's get to the equation. Now we know what it means, and we've established what is up, what is down. Okay. So now we start with the up, the positive, right? So that is this portion, and we're talking about force, right? So we're talking about apparent force. So that will be force, right? Apparent. Okay, that's up. And then the next, so this one is dealt with. The next one I'm talking about is another down, which is this. It's a down, right? You've seen that down here. So that's a force due to gravity. That's the weight of it, right? And the next, talking about this, the next is this, which is the forces acting on the surface of this small portion of fluid that we're talking about, right? So that's, and this one the negative, right? And then we have this acting on the larger surface here, and then this dp here. Let's put it somewhere. Okay, let's write it somehow. Okay, so this is F, and on the surface, right? So surface forces plus another F, surface forces, but the small surface, which is this size. Let's clean this up so we can see what's happening. Okay, so this side, yeah, the small sizes. That ends up moving the fluid up and down, right? So let's make it just ds, right? But then we know that force, let's use pressure. Pressure is what force per unit area, right? So if we want the force, basically we end up getting a PA, right? So that's how we end up seeing some P's and stuff. Okay. So that would mean that we have a F here, this up here, this F, right? So we have a PA and the area of that small layer, that small part of the fluid, right? Okay. What do we have again? And then we move on to the next. This FG here is weight, right? So if it's weight, that will mean that we have what's the name? Rho. If it's weight, then density comes in, right? And then we'll have G, right? Rho G, and then we talk about because we said our coordinate system was let's see, this where we have X here and then we have Z here. So meaning up and down is a Z, right? And then we are seeing that this force, right? This body force here, right? It gives some sort of potential energy, right? So that's why we have rho GH, right? So rho density, right, related to body force or gravity, right? Then this association due to gravity, because it has a density, gravity has affected, and it's the height that will tell the energy that it has, right? So because we're seeing there's a very small thickness here, we say dz, right? The thickness of it, dz, right? There's the body force that we're talking about, right? And then we have this one right here, which is already represented there, P, right? And then we have the P, small p, right? The small size of it. And then we have area, right? The area of it, the area of the small volume that we're talking about here, right? And now that we have this we can simplify it. We are seeing that the resultant force here, all the forces, because they're acting on it, and there's a static fluid, all these forces sum up to what? Zero. That will mean that all this sum up to zero, basically, in our process of deriving the hydrostatic equation, right? So now here we can divide through by A, right? First of all, let's eliminate some things. Okay. We're still the same if we divide through by area, right? So this one is out, this one is out. And then we'll have an area added down here. That will mean now we end up getting a P, right? Minus density, there's no P. You have G, and then dz. This dz are together, so let's write a wall. This means that a small thickness of the fluid, right? Because we are saying a coordinate system is xz, right? Yeah, so we have dz. So let's make it this way. This dz are together, a small thickness or something, right? And then we have area here. And what we have here, we have a P. We brought it out, and then we have a dp here again, right? Okay. This is taken care of by this. So now we still have a zero here, right? So we're now getting this rho g, and then small thickness dz. We have our area here, and then we have minus dp equal to zero, right? We can just multiply through by, what do you call it, -1, and then we get rho g dz. You can skip a lot of these steps, like if you actually know what you're doing, but we are doing here so that we can see what is actually happening. Okay. So now that we have this, right? We still have, do we have common term? All right, so there's supposed to be another area here which we missed. So there's supposed to be another area here. Why? And here there is, we're talking about what's the name? Before we actually even crossed out this, right? Still a force PA. This for this one is for this. So these together, these are together, and this ones are the same, right? Let's say we're trying to convert the force to pressure, right? So there must be an area, right? Yeah, there must be an area. Okay. There must be an area. So this cancels this out. So that's mean that we don't have an E here, right? There's no E here, and there's no E here. So we can simply take them out, right? Okay. So now that we have this, we are trying to find difference in pressure, right? So that will mean that if our aim is to find hydrostatic equation, right? Okay, so we divide through by density, right? So that will mean that we have G. Let's integrate first. When we integrate, that means all the small quantities go away, right? So that means I have rho, and we have G, and then because our coordinate system is x and z, we have what a z here, right? And what do we have here? This is the P, so we get a big pressure, right? P, we integrate a small pressure, right? We still have a zero here. When we integrate this, what do you call it? Zero, we get a constant, right? So that's what we get up here. Right? That's after integration, we get a constant here. So that's what we have. This is the basic form for the hydrostatic equation. But if you're talking about two different points, that's when we go on and see that we have, when divide through by rho, right? Divide through by rho, right? We end up getting let's see, this is how we're getting G and Z, right? And then we have a P on rho. It's a constant. This is the basic form. But if you're talking about the hydrostatic equation with respect to two different points, that's when we get to say that we have this. So let's see. We're now getting this rho, this P. Let's write it well. P, capital P. Okay. Okay. So that's why we say the differences in pressure. That's what actually give us that. So basically means that we're talking about two different points. Let's say point difference in pressure in point A and point B. That's what we go on and say we have this P, right, on this minus at, let's say, A. This is something else, right? That's different density. So it's a different point, and then we have a P. It's a different point. Let's say B. Right. Then that gives us this. We have G, and then a change in this height, a different point within the fluid. And then again, remember that there's a reference, right? The point could be, let's say, about yes, let's say, respect to a coordinate system. Right? So let's just map this here. That means I could have about B here, and have a point B here within this point, right? So different points within the fluid, but the height, right? So that means that we have Z A, right? That's the height at that particular point. Let's go with this. When we get here, what happens is that it can get a bit confusing. So G and Z, when you move it to the other side, we end up getting a P and a rho, right? So here becomes negative. Yeah. So that's what it means here. But then if we are talking about two different points, and then let's say we have a G here, and then let's say we have Z, let's say A, and then we have Z, B. Because this is constant, this expression here is constant, depending on system. We have a P, then we have a rho here, right? So if we're having this for, let's see, at because we moved it to the other, it's still on the left hand side, right? So we have a proposition A, right? And then we have this proposition B, pressure, proposition B, and this so density. And we're seeing all this is zero because in the same fluid, right? What happened is that we end up getting the G, you have ZA, ZB, right? And then we have a PB, and you have density, the same fluid. And then we have a PA, because they are moving, these ones move to the other side of the equation, right? That's why you have the equal to here. So PB, row on row, and then we have PA on row. So this right here is the basic form of the hydrostatic equation, and then it can be, this ones can come here because it's an equation. It can be every which way, it can be on the left and the right, but this is the basic form, right? Differences in pressure. Yeah. This could basically turn up to be this, where we have this row comes out, we have row, we have G, and we have ZA. Even if you get to this side, it's still the same, right? Dependence in pressure, PB with PB. And where we are seeing that this A and Z, A and B, should be subscript. This A and B, actually different points within the fluid, right? Different points within the fluid. Alright. So yeah. So this is the last test of understanding that we have. The last question of test of understanding. Alright.